Can we restart, please? Thank you. So I think what we're going to do with the posters, we're going to also give a prize for the most creative attachment of a poster to an easel. Some of them
multiple points of attachment are plus,
yeah.
Right?
So if you come back to us and afterwards let us know which attachment you found best, we'll do something.
You can tell this is a meeting of engineers. That's all I can say.
All right, so session number 2 is a session on SDN routing and peering, and yes, we understand not all of them are super related, but they're more related to each other than to the other session topics. So this is why they ended up here, and we have 2 full papers again and 2 short papers. First one is Marco.
Okay, hi everyone. So Marco Chiesa from University of Leuven. This work was led by Tan Nguyen, who couldn't present this paper here today, and it's a joint work with Marco Ganini. So in the recent years, we saw that many SDN systems demonstrated its value of centrally controlling the network and proved many advantages of doing so. Like others, we observed that these systems operate by frequently updating the network configuration, either in a periodic way or in response to link failures, load changes, or dynamic conditions. So as such, we believe that updating the data plane in response to dynamic conditions of the network is a fundamental operation for any SDN system. We distinguish between 2 types of updates. The planned updates are the ones that somehow can be scheduled by the operator. And for instance, if an operator wants to change the policies, and this is an operation that is planned, then there's no really tight time constraints in order to perform this operation, and it is possible to plan the update in such a way that it's as seamless as possible without disrupting the network performances. The other type of updates that we consider are unplanned updates. These updates arise in response to network events, to unexpected network events. Such updates such type of events can be network failures, changes in the load of traffic, and network attacks. So let's consider a situation in which we are using a routing in our network, and at a certain point there is a network event which can be a failure or a change of loads in the network. So what typically happens is that the network operator designed a protection routing which is used in response to such events. Such protection routing is typically based on just local information at the switches, so it's not globally optimized. At the same time, when the network events happen, it triggers the network controller in the network, which computes a globally optimized routing, and which has to be reached in the network. So in this talk, what we want to do is, in order to reduce the period in which a user would experience a worsened network service in the network, we want to perform this update from the current routing, which can be a protection routing, to the new optimal one. So while it would be tempting to perform the update as a one-shot operation, this can be a potentially dangerous operation. So in this example, in fact, we shouldn't forget that the network, we cannot alter the fact that the network is a distributed system, and messages are not guaranteed to be received at the same time, and the switches cannot synchronize to perform an update exactly at the same time. So, for instance, in this example, in which we want to move from this current configuration to the target one, in which we are moving the blue flow from one path to another one, if switch 2 updates its forwarding state before switch 5 does so, we will have black hole traffic at switch 5. So another type of problems that can arise while updating the network is the following one. So let's consider again this example in which each link has a capacity of 10 units, and each flow requires 5 units of a capacity. So when we want to move from the current configuration to the target one, if we update the blue flow, so in this example, we only move the green and blue flow. So if we update the blue flow before we update the green one, then we'll get a congestion on the link 1, 2. So and this would mean that packets will be dropped in the network. So there were actually many works that dealt with this kind of problems. And most of them actually advocates for a centralized approach in which there is an SDN controller that actively drives the update, the update by performing several steps. The SDN controller will schedule each step of the update, will send the rules updates to the switches, and will pause every time it is necessary to receive an acknowledgement from the switches and interact with them. So in other words, what we see is that in these approaches where the centralized actively drives the update, the switches only behave as remote nodes that the controller only writes states to and is notified from. So this interaction among the controller and the switches is often inefficient due to the inherent delays that exist between the switches and the controller. So another related work is the Time for paper from Infocom 2016, in which the authors developed try to synchronize the update. So a sophisticated technique for performing an update at the same time on all the switches, but this kind of system still can't achieve perfect synchronization, so still there will be anomalies during the update. In this talk, we argue for decentralizing the update responsibility to the switches. So we present Easy Segue, which is a decentralized update mechanism for performing fast updates in the network, which is a crucial operation in case of failures and changes in the load of traffic. Our technique leverages the idea of moving some of the logic that is typically performed in the controller to the switches. So we want to move as the simplest possible logic to the switches and perform the update there. So that the high level how the Easy Segue works as follows. So we still have an SDN controller which is the central point, and it receives as an input the current configuration and the target one. It first detects which are the flow dependencies. So as we saw in the previous example, in certain cases we had to move one flow before another one. So this operation, computationally expensive operation, are still performed at the controller. So after it detects these flow dependencies, it will compute a partial ordering of the update operations, which is a minimal information that will be sent to the switches. Upon reception of this information, the switches will coordinate among themselves and use their local information and global state in order to perform the update. So we believe that this separation of concerns actually removes the bottleneck, the computational and the communication bottleneck that exists among the controller and the switches, so as to allow us to perform a faster update. So let's now have a closer look at these steps that I just described. So at the beginning, the SDN controller receives the initial and final configuration, and it tries to detect what are the dependencies among the flows. So it builds a dependency graph. A dependencies graph is a very simple structure. For each link in the network, I won't show all the complete dependency graph, but just a subgraph of it. So for each link, it creates a rectangular vertex. In each rectangular vertex, we keep track of how much spare capacity there is on this link. So for instance, on link 1.4, we have 5 units of spare capacity. So recall that we have each link has 10 units of capacity. For each flow operation that needs to be updated, we'll have a node in the graph. We then add arcs from links to nodes, which basically capture the fact that a node operation requires some capacity from a link. So in this example, the green operation, which is moved to the link 1.4, requires 5 units of capacity from link 1.4. And we use blue arcs to capture the fact that when you move a flow, you will release some capacity. So for instance, if you update the green flow, you will release capacity on the link 1.2. So why is this structure helpful? So for instance, from this dependency graph, we can understand that if we update the blue flow, we need 5 units of capacity from link 1, 2, but link 1, 2 has no spare capacity. So if we perform this operation, we would move the blue flow on the link 1, 2, and we would create congestion. At the same time, we can see from this dependency graph that the green operation is safe, as it requires 5 units of capacity, and there are 5 units of spare capacity on the 2 links, 1, 4 and 4, 2. So once this dependency graph is constructed, the controller will compute some information that is used to schedule the update in the network that will be used by the switches. And this information is actually an assignment. It's a partial ordering of the flow update operations. And it boils down to just assigning priorities, 3 types of priorities to the flow update operations. So let's have a closer look at what it means. Why do we need to assign priorities to the flows? So in this example, I added a gray flow. I don't want to go to spend too much time of this example, but the main insight here is that if you first update the gray flow, you would reach a state in which you cannot anymore update either the green one or the blue one. So you would have to deal with some congestion. But if you were to first update the green flow, then you could update the blue one, and in the end, you could update the gray one. So what I want to say here is that there are some updates operation that should be performed before others. So these are these flow dependencies that we have to deal with. So the main idea here is that we have to assign priorities. So in this case, we would assign a lower priority to the gray flow so that it would be performed as after the other ones. So once this partial ordering is computed, we push this information to the switches. And this operation is performed just once. After this, upon reception of this information, the switch will coordinate among themselves in order to perform the updates without requiring any interaction with the controller. So let's have a look at how the switches can actually coordinate and perform an update. So we want to move again from the current configuration to the target one, and we move only the blue flow. So the path, when we want to install the new path, we install this path in the upwards direction. So we start from the endpoint, so the node 3, and node 3 will send a message to node 5 and notify him that it is possible to start the update. And node 5 will install the forwarding rules to forward the traffic on this new path. So this information is sent upwards until it reaches the source node. Once the source node receives the acknowledgement that the path is installed, it will start moving, forwarding all the traffic through the new path. Once we are forwarding the path through the new path, it's now safe to remove the old one. So what happens is that we will remove the old path by sending a message downwards along the old paths. So what happens is that we'll remove the old paths downwards, and we finally have the new path installed. So in order to achieve fast updates, we use a technique that we call segmentation. So if you look at this example, you will observe that node 2 is in common among the old and the new path. So this means that we can actually partition this update in two independent updates, which can be performed in parallel. So for instance, we could perform the first segment. So we divide the update in 2 segments, and we can perform the leftmost independently of the rightmost. So for instance, in this case, we could update to the new path on the rightmost segment without creating any anomalies, forwarding anomalies or anything. And at the same time, we could update the leftmost. So this technique allows us to further speed up the updates during in easy segue. So I just show how the switches can coordinate and update. So still, we saw that there are some flow dependencies, and I didn't show how the switches can actually schedule the updates, that is, decide when they want to move to perform an update operation. So as I said, the switches receive some priority information, and then we'll actually use this information to schedule the updates. So they will move a flow only if first there is enough spare capacity on the link on which they want to forward this new flow. Otherwise, they would incur some congestion. And second, they would move a flow only if by doing so, they will not preventing any higher level priority flow update operation in the future, which is still not available at the moment. So we performed we evaluated our system, EasySegway, by running a large scale simulations. We compared our system, EasySegway, against a centralized approach, in which basically we want to perform the same update, but in this case, the update is coordinated by a central entity. In each simulation, we measure the total update time, so how much time it takes to complete an update. And the setting was the following one. We evaluated our approach on 6 different topologies, on each from rocket fuel. So on each topology, we assigned the bandwidth between 1 to 100 gigabits per second capacities, and we did so based on the standard Cisco recommendation that will assign the inverse of the capacity to the weights of the links. We gave the ideal scenario to the centralized approach by placing the controller at the centroid of the network so that the latency among the switches and the controller is as small as possible. And we generated flows based on the gravity traffic model. And initially, each flow is routed among shortest paths via a random node that is chosen at random. In order to compute the target state, we actually failed several links in the network so that the flows will actually be required to be updated on new paths. And we performed 10 execution of these simulations for each network. So the results shows that EasySegway is able to reduce the update completion time by a factor of roughly 1.52, 15%, 50%. So let me wrap up what we discussed so far. So we, in this talk, we explored the possibility of delegating the responsibility of performing a network update to the switches, which is a fundamental operation in any network in which there are failures or dynamic events. So we proposed EasySegway, which is a decentralized mechanism for network updates that tries to achieve faster updates. And in doing so, our technique leverages the idea that we could move some simple yet crucial logic from the controller to the switches. In doing so, EasySegway actually enables the switches to engage as active players in the network updates. And while they perform the update, we want to guarantee that no forwarding loops, no black holes, and we try to avoid congestion during the update. In the simulations, in the evaluation, we showed that we can actually reduce the update time by a factor of 1.52. And our ongoing work is will try to address to actually perform better evaluation of the system beyond just large-scale simulations. So we are actually evaluating our system in Mininet, and we are performing a feasibility test on some real OpenFlow switches. Finally, we also want to formally prove that the distributed algorithm that we are proposing is actually safe. All the distributed properties that are typically proved in these cases, so safety, liveness, correctness, completeness. So that's it. Thanks for your attention.
I am Dirk Kutscher. So when I read the paper and I think it was really interesting. So like intuitively, so the approach makes sense and you are able to demonstrate this in your simulation. Since this is the applied networking workshop, do you see any barriers to real deployment? So I'm thinking about implementation complexity, maybe what happens if things go wrong, these kind of considerations. Is that part of your ongoing work? Or?
Yes, this is part of our ongoing work. So far we actually tested it on a real Centex switch, and we measured the complexity overhead that is required in order to run our algorithm. As I said in this talk, we really try to move the lowest possible amount of computational complexity to the switches. So actually we saw that it scales to we don't see a computational bottleneck in the switches in order to perform this operation. We still perform all the complex operation at the controller at the beginning, and we really just push minimal information, and the switches just perform very simple operations, like they check if there is enough bandwidth, and they will move a flow only based on a priority queue basically. So to answer your question, we actually saw that it doesn't seem to be we still don't see any bottleneck right now, but it may be that in the future I mean, we still plan to further complete our. Okay, thanks.
Can you speak into the microphone?
Daniel Raumer. I have two questions. One question, but you are relying on two assumptions. Your flows have to be static, and the traffic you send has to be quite unelastic. So do you have plans to include any dynamic changes in the flow capacities? Okay, so yes, the assumption is correct. We can actually also deal with like the fact that the flows will change in sizes. So during this talk, I just showed flows that always have the same size for the sake of simplicity. But actually in the target configuration, it can be that the flows will be larger, smaller, whatever. So actually this is an interesting question. And the one thing that we actually would also like to improve is this fact that when you put the control of the network update to the switches can much more quickly react to dynamic changes in the network. So the flow sizes of any dynamic condition of the network can much faster be detected by the switches. So what you are saying is actually correct. That so what I want to say is that our approach actually would be even better than a centralized one in order to deal with very dynamic traffic patterns, because the switches actually will see this network, can collect statistics on the spot, and will apply the more suitable operation as fast as possible. Thank you.
Thank you.
All right. Are there any other questions? Okay, well, thank you.
Thank you.
All right, next up is composition of SDN applications.
Yeah, I can also bring my own. Yeah.
This one.
Yeah. Yep.
So the beginning.
Yeah. So, yeah. So I'm presenting composition of SDN applications and chain options and challenges for real-world application.
Can you keep closer to the microphone for the streaming people here?
Yeah, probably need to.
You can take it in your hand.
Yeah, you could just lift it out.
It's probably a bit too low for me. Okay. Yeah, that looks better, and I think you can hear me better now, right? So yeah. I'm Arne Schwabe, and I did the paper together with Pedro and Holger. And I will just dive in and just give a motivation example at the start. Assume you have your normal network and have a firewall in there and also a load balancer. And now you think, well, this is nice and fine, but I want to do all the modern trends and modernize my network. So you start replacing your firewall and your other box with SDN. So you replace your SDN switch with an SDN switch, an SDN application, and do the same with a load balancer. Now, you look again at your network and say, oh, instead of 2 boxes, now I have 4 boxes. And say, well, that's not what I wanted. So you start virtualizing the application together on one server. But you still have 2 switches which are basically the same and do the same. And you ask yourself the question, can I combine these 2 switches? That should be easy, right? And I think that's the idea what we want to talk about. How can I have this 2 SDN application running at the same time? And first, I will talk a bit about the general approach here, and then I will come to OpenFlow in specific. When I talk about SDN application, I will assume you have like this existing application that you just want to use together. So,
stand near to the microphone.
No, nearer to the microphone. Okay. First, we look what an SDN application actually does in a bit simplified way to look at things. Basically, something happens in the network, a network event like a packet in, then the application does some processing and has an answer to that. So, and that results in a new network or a new switch state. So, simplified, we can say an SDN application or SDN module is just a simplified stateful function that takes in some network events and responds with some network commands. Let's look at that again in our simple example. So what happens here? Again, the packet in comes in. We get a network event. The firewall application reacts to that by saying, okay, this packet is fine, forward it to the next switch. It then again gets packet in, and the load balancer decides, okay, so the fine packet I forward it to some of the backend servers. So that's what's happened here. And now, what's our idea to combine this? Basically, before that, also, if a packet is coming in we don't want, the firewall will say something like, drop the packet, and there's less. But what's the idea here to combine that? Well, we have this packet. We ask both of these modules what to do with the packet. Both will give us some answer. The firewall will just answer forward it or drop it. And in this case, we would combine these 2 to 1 forward command and just go with it. And similar, if the packet is bad, we get a drop from a firewall, prioritize that, get that to the server. So that is the thing we're aiming at our simple example without modifying this application. So before going into the more general case, also another idea is to just ask them one after another. So instead of combining them at the end, just gives the input of the first SDN application to the second one. In this case, it would be asking the firewall, are you okay with forwarding to port 7? And the firewall would say, yeah, I'm okay with that. Or again, drop it, and then just take the output of the second module as our combined output. So that's nice and fine what we want to do. How does it actually look in practice? Assume that you now, instead of these 2 switches, have only 1 switch, which is we want to aim up, and you want to compose the application. First, we'll state that without any additional logic. So what would happen if you just run both applications at the same time and then don't care about it? That's basically what you can do with an SDN controller. You just install your SDN controller and install all SDN application on that, and let all them do the stuff. But backend, yes, you get the event in. Both will process them and send some commands to the networks. Maybe the first module is faster than the second, so it will send its commands first, and after that you get the second. So what happens here is that you get 2 different switch states, and also the order in which these commands are happening is not predictable, so you end up with transition states. The commands of your application can conflict because they're probably not programmed in a way that they care about other modules, and also their outputs might conflict. For example, as in the previous example, one might say drop, the other might say forward. So depending on the order, you might have a small window where you forward traffic, or a large window where you might forward traffic, depending on the drop or the forward comes first. And how do you solve that? The idea here is instead of letting all applications do their work on their own, introduce a function or a layer that harmonizes all this inputs. For example, this could be part of an SDN framework, but also could be like a SDN hypervisor. An example would be like only allowing certain SDN modules to work on certain parts of the network. So how would that look in this scenario? Well, everything happens as before, but instead of relaying everything to the network, this harmonizing function just collects every network output, and then creates of that a new set of commands that will hopefully work on the network, so that there's no problem there. And the same can we look at the serial composition, how that work? Well, as we said, we just give the output to the input of the new function. That works. The new function will then add the network command, but it has only one minor, or actually major caveat. That is, it absolutely changes the input of the second function. Because if we want to reuse a function, we can't just take network commands as input, because it doesn't expect that. So how can we solve that problem again, or how can we make that work? Well, we can say, well, we cannot make the function, we cannot change our SDN module, but maybe we can present it something that it expects. So we can try to get from this network commands to some input event, and try to represent as much as possible in that event. The problem is not everything might be presentable. For example, an input port. I will give you an example how such a function could work. Assume you have one physical switch. Sorry. And instead of, and as a approximation function, you say, okay, I represent that as a virtual topology with 2 different switches, and assign one of the SDN module to each switch. So whenever a packet comes in, you give it to the first application, and then which then will do something to the packet and say, okay, forward it on port 7 or port 6 or 4. And whatever port you output there, it outputs, gets the input port of the next switch. So what do we lose here as information is, for example, well, the output port of A becomes input port of B. So B loses all information about the original input port or about the original input of this packet. So it's, as I said, it's only an approximation, but it works fine with an existing module. So after giving this overview about how to work with general composition, we go a bit more detail for OpenFlow. Why OpenFlow? Well, OpenFlow is kind of the de facto standard for SDN. There are competing ones, but at least in academia, there is basically only OpenFlow which people use. So there's a strong desire to reuse it also for composition. The question is, does that actually work? Mapping events and network commands to OpenFlow terms is rather easy. We just have packet ins and flow mods and packet outs. And we'll just dive in and look at the first example of the parallel composition. What actually happens there? So it looks almost the same. And at some time, one of the module responds. So what's the problem here? Since we don't know anything about the internal state of A, we don't know if it responds or when it responds. So we have no idea no idea how to collect all answers. So the only thing we can do is like work on these flow mods and pass them on, and maybe after some time also A responds, and we can do the same here. So that is already, even with this harmonizing in place, we are already limited because we do not have any relationship between this network commands and packet ins. So we can't have this take all inputs, combine them in this harmonizing function. That makes this harmonizing less useful or more difficult, but it might be okay. For example, if we just say, yeah, part of the ports or part of the network is controlled by one application, and part is controlled in another application, we can just avoid that problem because the synchronously managing these events is not a problem there. The other problem that is great that we might get this transition state even with this harmonizing function. And another thing that often happens in OpenFlow application is that they sometimes decide, now I want to now I want to send an event without any packet you can relate that to. So now we had what is problematic in parallel. Let's look at serial in OpenFlow. While it's an input event, we basically only have the packet in, and that contains only an import and a packet. So there's not much data you can communicate to this application. And what we can do as a workaround is to do everything the first application wanted to do and apply that and somehow mangle that into the packet. We can in this packet of the packet in. And other properties, which are network commands, are basically lost. If you get if the first application spits out a flow mod, we can't transform that magically into an Ethernet packet, so we have only this chance to drop it. Considering that all, how can we make OpenFlow work? That's something we did in our research project. Well, first we added a custom header, because custom header is always cool, and added transaction IDs. So we modified all these SDN controller frameworks to basically tell us when they are done processing this packet in, so we can track this and get this relationship between the packet in and flow mods or packet out back. then we also need to restrict the behavior of what this application can actually do, like not sending these commands at a random time, only replying to an event. Those are some minor, also some other restrictions. And also, since the serial composition is so ill-defined in OpenFlow, more concentrate on doing only the parallel composition. What are other people doing, or what can you do else? There are some frameworks that take a different approach, for example, that are especially designed to work in that environment. For example, like SDN programming languages like Paretic, where every input is a policy and every output is a policy. So you have always can match and mix that like you want. Then there are network hypervisor which do this harmonizing, like partition the network, like application A is only allowed on VLAN 1 to 5 and B is on 6 to 100. And if an application tries to do something else, we just drop it or ignore it, or modify the flow mods to restrict to only that case. Then there's also papers like CoWeather which claim to have solved composition. Unfortunately, they don't tell in the paper how they are trying to handle this this problem of not being able to relate packet-ins to the commands, and the implementation they provide is very basic and basically assumes everything that needs to be composed is known at the beginning. So, as a conclusion, we can say composition can work in the real world with a lot of asterisks. The behavior of the APIs you're using is very important. As we've seen, OpenFlow works very poorly. You can modify it for composition so it works, but you end up with a custom protocol doing that, and also which leaves still much to desire. So if you're really into that stuff, it's better to use or go into a fully custom direction. I think that's that, and yeah.
Okay, so we have plenty of time for questions.
Well, I'm surprised that the SDN topic, which is so hot, is getting so few questions. So I'm not an expert, but have you looked at P4 and whether it can do something for you that OpenFlow can't? Since you had you were discussing some limitations you were seeing with OpenFlow.
Actually, we haven't looked at P4 because that's not really much used or known in the research community. So,
okay.
So sorry, no idea about
that's fine.
Actually.
Dirk.
Yeah, that was actually also my question. But okay, so you concluded with say like you would recommend extending the OpenFlow protocol to support your composition use case better. I mean, apart from like these protocol improvements, can you like articulate say like the fundamental say is there anything fundamentally wrong with like the OpenFlow like flow-based match action approach, or would you recommend going for like a say totally different SDN approach, so something in this direction that you can recommend?
Okay, OpenFlow is not a bad protocol. OpenFlow is a good protocol designed to be a southbound protocol from a controller. As such, it is designed to have one controller to one switch, and it does a good job at that. Putting composition on top of this is what breaks the protocol, because it has all these things you need for cooperation of multiple clients. Breaks that protocol. So it's a very good protocol for this southbound interface. but it really breaks as an application interface protocol with people trying to do.
Okay.
Hi, Colin Perkins. So is the problem that we have insufficient formalism for the applications running in the controller rather than the problem being the protocol?
I mean,
the OpenFlow control protocol.
I mean, in the controller, it depends. A lot of the APIs inside the controllers are like very shim layers on top of the OpenFlow abstraction. So you run into these problems. Some of the controllers also provide higher level APIs that then do some internal representation, but often you can also access the lower levels on the controller and just say, I want this flow in the networks. And if your application doesn't care what the other one, you are running in the same problems. So, and having these lower level APIs in the controller actually makes implementing such a composition logic in this controller very hard, because you have to deal with all this strangeness that basically is lower level from OpenFlow inherit.
Right. So can we formalize this some way to make this problem more tractable, or is it inherent in the domain?
I mean, it's more like basically this not knowing this. One of the biggest problems is with not knowing if an input event or how to handle some traffic, because OpenFlow assumes you are reacting always to something, or you do it on your own. So there's always some hidden state how the network should behave, how the flow should look like. That is only triggered on a need-to-know basis, like basically for the switch, because the switch doesn't care. It's like a dumb switch that only does what it says. But in the point where you introduce this composition, the composition logic wants to know that. But with OpenFlow or others, this I only do something when I need to. You either need to query this application, but that's not something that has been designed like for these kind of protocols.
Okay, so the reason this problem is hard is because there's hidden state in switches, which and it's not just a purely compositional approach you can just model. Is that right? Okay, thank you.
All right. Any other questions for the speaker? Thank you. So we have two short papers. Same rules apply as earlier. Clap after 5 minutes. While our next speaker is getting set up, we mentioned the barbecue tonight, and some people tried to register and told us it was booked, fully booked. They've just now added some capacity, so there should again be tickets available. So if you want to go, you can try to register again. I think they said they added 30 seats. There's more than 30 people in the room, but if not everybody goes, then they won't run out. They also said that they won't have security guards. So even if you don't register, you might be able to get in. Although they said they have the food quantity is sort of limited by the amount of registrations they have, but they have sufficient alcohol. So do with that information what you will. You look familiar. So I see 6 posters up. That means we're missing 3 posters at the moment. Is there anybody who hasn't put their poster up yet? All right. You might want to do so in the beginning of the lunch break. Okay. Do you need any materials or? Okay, good. So you have 2 posters. Hello? Yes. 2 posters. Okay. That means I'm still missing 1 poster. Stephen.
I didn't know about the posters.
Oh, come on. stand next to your empty easel and anyway,
we've got pens, papers, and notepads, right?
All right, go.
Thanks. So this is joint work with TU Darmstadt and the Hebrew University of Jerusalem. If we look today at the internet peering ecosystem, we'll see that internet exchange points are growing in importance. At large IXPs, we see accounts over 600 members that announce roughly 200,000 of IPv4 prefixes, and with insanely huge amount of peak traffic volumes, which are comparable to large transit networks. One of the key benefits of IXPs is that a single link connections already opens a wide spectrum of peering opportunities for a new connecting members. Once physical connectivity is established, it is, however, it is necessary to establish peering among other members to exchange routing information via BGP, which at large IXPs may be will add some management complexity. In an ideal world, in an attempt to ease this situation, IXPs are providing route server services which dispatch routes among the members, and these are centralized entities, components. However, in order to make use of these route servers, the members have to disclose their routing policies to the IXP. From some conversation that we had with operators, we detected that this disclosure of information may deter some networks from make use of the route server. So in our ideal world, we would like to design a centralized route server system that will dispatch routes without learning anything about the member policies, while still dispatching according to the member policies. So in order to tackle this challenge, we use secure multi-party computation, which is a subfield of cryptography. There is a very simple, nice classical example, the millionaires one, in which two millionaires want to learn which one is richer, but they don't want to reveal to learn the net worth of the other. So the SMPC is this tool that allows you to solve this kind of problems, that is to compute a function without revealing the input. So in this case, this problem can be solved by simply securely evaluating a comparison function and producing just the output. So what we did, we designed a six-pack, which is a route dispatch, logically centralized route dispatching mechanism, which basically emulates a full mesh of BGP session in a privacy-preserving manner. We leverage SMPC in a setting in which we have only two parties. So we split the route server into two entities that runs the SMPC protocol and are operated by two non-colluding entities. The main challenge in SMPC is to make things scale for practical runtime. So our main efforts was to use sophisticated techniques in the SMPC in order to achieve something that we believe are practical runtimes. So for each route, in order to be dispatched, we actually need around 0.6 milliseconds, and we require negligible amount of memory and bandwidth. Thanks.
All right, I see we're going to have to gradually make these slots shorter. Everyone's finishing early. All right, next up is computing customer codes. If you're the last lightning talk, you'll have 30 seconds.
No. So I think lunch will be outside. They're setting it up, and then have lunch, and the people with posters can hang out next to their poster. I think originally we said that if you presented your lightning talk, you should maybe stand next to your poster in this break, and if you are presenting your lightning talk in the afternoon, stand next to your poster in the afternoon break. But we can't force anybody to stand next to their poster or prevent them from doing so. So do what do what you will. But so the idea is also that people with posters get to look at other people's poster. And lunch is about an hour, so we come back here at 1 o'clock. Just tell Colin when you want the next slide. Maybe it's out of battery. Well, the thing is.
So I'm Laura from Iowa State University, and this talk is about computing customer counts of peering networks. Is it?
Right into it.
Okay, okay, so now it works, okay. Okay, so yeah, the customer count of AS is defined as the set of ASs that can be reached from it following only the provider to customer links.
If you point it at your mouth, it works better.
Okay, so in this work we focus on peering networks that participate at multiple IXPs. So we ask the question: do these networks have identical customer codes and also announce identical customer code prefixes at different locations? By answering this question, we can understand if the routing policies of peering networks are location dependent. So to answer the question, we have developed a method to compute location dependent customer codes of peering networks, and we make use of BGP data archived by PCH. PCH operates root collectors at over 100 IXPs around the world. And they provide the BGP data online. So we download the routing table snapshots of all the PCH collectors on March 1st, 2016. And so using the snapshot of a PCH collector at a specific IXP, we will be able to compute the location-dependent customer count of a partial VP of every partial AP at the IXP. So by partial VP, I mean peering network that peers with PCH collector and also only announce customer routes to the PCH collector. So basically, if a network is a partial VP at multiple IXPs, then we will be able to compute multiple customer codes for this network. And all those customer codes may or may not be the same. So we want to analyze those different customer codes to see if they are location dependent. Yeah, so basically we use March 1st, 2016 PCH dataset, and we computed over 5,000 LDCCs for over 3,000 partial VPs. So, and some of the partial VPs only have one, is only present at only one IXP, so they only have one LDCC. But we are interested in those peering networks that have multiple LDCCs. So basically there are 1,158 networks with 2 or more LDCCs. So we analyze those different LDCCs belonging to the same network, and the results are the following. So we see that 44.2% of the peering networks have non-identical LDCC sizes. So they have the size of their customer codes are different at different locations. And also 58.8% of them have non-identical number of prefixes in their LDCCs, which means they announce different prefixes at different locations. So the results basically show that peering networks often announce different prefixes at different locations, and they have different customer codes at different locations. And we also look at the business types of those peering networks. So we use peering DB to look up the business types of those networks, and we are able to find find the business types for 956 networks. And most of these networks are either network service providers or access providers or content providers. So these are the three main types of networks that peer at IXPs. So for each of these three network types, we calculate the percentage of networks that have non-identical customer cone sizes at different locations, and we also compute the percentage of networks that have non-identical number of prefixes in different locations. So the percentages are shown here for each of the three types of networks. For NSP, both percentages are higher than 50%.
All right, thank you. Lunch is outside. Be back at 1.